Okay, so the first question here is asking about hierarchical clustering, and the first clusters to combine is always the one with the smallest distance. So find the smallest number here, and it's 1 here. 1 corresponds to the distance between E and F, so that's why we are combining E and F. The next question is asking for the distance between this EF cluster and A. So the distance between A and E is 6. The distance between A and F is 7. Depends on whether it's complete linkage or single linkage. If it's complete linkage, then it's a max. If it's single linkage, then it's a min. In any case, here is max, so it's 7. And here it's asking to repeat the same thing a few times. So we saw the first one, we combined E and F. Next, we combined the one with the next smallest number, but then we need to first figure out what are the distances. So let's do this here. The distance between A and EF, again, is the max between these two. So I pick this one, this is gone. The max between these two, this is gone. This is gone, and this is gone. So now we know the new table with EF combined. Then we find the minimum distance now. So there is 3 and there's 3, so you can combine either, but also you can combine them at the same time. So this 3 correspond to A and B, so AB is combined. And this 3 correspond to D and the EF combined cluster, so DEF is combined, so the only remaining one is C. Okay, move on to the next set of questions. So these are k-means, 2 means, and at the beginning, the cluster's centers are 5 and 10. So figure out which numbers are closer to 5. 5, 7 is closer to 5, and 8, 10 is closer to 10. And I want the cluster center in the next iteration to be 5. So the cluster center of this is 5 or this is 5. Obviously, this is 5. So at the moment it's 6, so we need one more. So let's put x here. So the cluster center between x, 5, and 7 is 5. So it should be 3, but let's write it down. X plus 5 plus 7 divided by 3 should be 5, and solve for x. X is 3. Okay, and here, how to make the next cluster center 7? So again, we repeat the same thing. This is 5, 7, this is 8, 10. So it seems it's more reasonable to have the cluster center of this cluster 7. So let's put another x here. So we can solve for x. X needs to be 9. However, if x is 9, x should have been put into this cluster. So that's why it's not possible. Of course, you should solve for the other one, x 8 and 10. And the center is 7. When you solve that, you will see that that x belongs to the first cluster. So in either case, it wouldn't work. So that's why it's impossible. Okay, move on to the next set. How to do projection, just formula. So 24.11 divided by 11.11 times 11. So that will become, these two multiply these two, so it's 6 divided by these 4, so it's 2 times 1, 1, and that's 3 and 3. So this answer. The second one here has length 2 and it's projected onto this. So basically, it's whatever that is, projected down. The length is 2 in this 1, 1 direction. So the only thing to do is to make this direction, say, TT, should have length 2. So what's the length of this? It's just tt dot tt square root, and this is square root of t squared plus t squared is 2. So basically t squared plus t squared is 4. So t squared is 2 and t is square root 2. So that's how we get square root 2 and square root 2. And here we want to find the projected sample variance. So first you need to project these two onto 1, 1, 0, or you can just find the magnitude of the projection. So magnitude of the projection is just x transpose u. So this multiply basically this dot product this. So the first one is 1, the second one is 3. So now you find the two magnitudes, and then you substitute into whatever this formula is. And this is n is 2, there are two numbers, and sum up all of them. 1 minus mu is the average, so the average of these two is not 1.5, 2. So 1 minus 2 squared plus 3 minus 2 squared. So this is 1 plus 1, 2. 2 divided by 2 is 1, so that's why the answer is 1. And repeat the same thing. This is exactly the same. This dot this is 2, and this dot this is 4. So their average is 3, and half of 2 minus 3 squared plus 4 minus 3 squared. This is 1, and 1 again is 1. Okay, so move on to the next set. We have an x transpose x. That's a matrix like this. We want to find one particular entry. Which one? So row 30 and column 60. So we want something multiplied this to get row 30. So it should be all 0 and only a 1 at position 30. If that's the case, then this row multiplied by the first column, it will be all 0 multiplied by other things, only 1 multiplied by the 30th entry. So this is this is row 30 first entry. And again, repeat the same thing. You basically, what you get is the entire row 30. And then you should post multiply something as well. So 0, 0, 0, say there's a 1, and everywhere else is 0. That 1 should be at position 60. And so we have this vector multiplied by this thing, and it's only picking up the 60th column, and this thing is the 30th row. So combining them, you only get the entry at row 30, column 60. So that's why this is the answer. So of course you can transpose this because x transpose x is symmetric. So row 60, column 30 is the same number basically. So moving on to this, how to represent the sum of row 60. So first we want to get row 60 now, not row 30. So we want all 0 and there's a 1 at position 60 multiplied by x transpose x. And for the same reason, we get row 60 here. Sorry, row 60 here. If you do this multiplication, and if you post multiply it by all the ones, then you are just saying this entry multiplied by 1 plus this entry multiplied by 1, basically summing them up. So that would be the sum of row 60. So that's why we have this expression here. So again, since it's symmetric, row 60 and column 60 is the same. So you can transpose this expression and to get this. So of course, as I said, column 30 is the same as row 30. So exactly same question, replacing 60 by 30. Okay, so let's move on to the next set. We have phase images with principal components, the eigenphases, and we want to reconstruct the phase with the first few principal components. So let's write down that expression. X, the original image, can be reconstructed by, let's not write the sum. So by U1 multiplied by this image plus U2 multiplied by this image plus U3 multiplied by this image. That would not be right. You need to, this is a number, so you multiply it back by the eigenphase. So that would be reconstructing the image. Let's actually try it. So U1 is 100 multiplied by 123. You get 1 times 100 plus this multiplied by this, you get 2 times 010 plus 3 times 001. It's actually 1, 2, and 3. Okay, so here we are asked to reconstruct with only one principal component, so we need to find the, the principal components in the correct order. So this is PC1. The one with the largest eigenvalue is the first component, and second one is with the second largest eigenvalue. Similarly for this one. So with only one principal component, we only want the first term. So that's why it's 100. With two components, we want the sum of the first two. So it's 120. And yes, 120. Okay, so now let's move on to the search problems. So here we start with integers between 0 and 6. And every time you mod 7, so basically all of them are possible. And we're doing BFS. And one thing that's slightly different from what we did before is there is the assumption that we keep a list of visited states. So the same state is never in Q twice. So keep that in mind, and let's start. So the initial state is 0, and you would dequeue that state, and you would include successors. Successors of 0 is 0 plus 2, which is 2, 0 plus 5, which is 5. So that would be the successors, and we're keeping track of a queue. So this is our queue. And then with DQ2, include the successors. One of them is 4. 2 plus 2 is 4. 2 plus 5 is 7. 7 mod 7 is 0. So 0 is DQ'd already. So again, the same state is never in Q twice. So we're not going to add that. And then continue. DQ5. 5 plus 2 is 0. Again, 0 was in the queue, so we are not adding it. 5 plus 5 is 10. 10 mod 7 is 3. So let's put 3 here. And DQ4, 4 plus 2 is 6. 4 plus 5 is 9. 9 mod 7 is 2. 2 is here. So we're not adding 2. And DQ3, 3 plus 2 is 5. 5 is here. 3 plus 5 is 8 mod 7 is 1. Put 1 here. And now we DQ 6. The goal state is 6, so we don't need to DQ 1. So that's why the answer is 0, 2, 4, 3, 6. Yes. So we repeat the same thing for DFS. So we are adding to the front, and we're pushing to the front, and we're popping to the front, from the front too. So start with 0, pop 0, and what are the successors? 2 and 5. And pop 2, the successor of 2 is 4 and 0. 0 is here already, so only add 4. And pop 4, 4 is 6, put 6, and put 4 plus 5 is 2, so just put 6. And pop 6, we're done, because the goal state is 6. So that's why we have 0, 2, 4, 6, which is this. Okay. So the next set of questions is the large tree. So I think I did it in the last lecture, so I'll repeat this quickly. You start with 1, so you need to start with a small tree and get the pattern, and then you will see what happens here. So start with 1, the successors are 2 and 3, and then 4 and 5, 6 and 7, 8 and 9, and so on. basically you need to see the pattern that this is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, and so on. So at here, 2 to the power 10, sorry, 2 to the power 10 would be this number here. So now which one are we doing? So BFS first. So BFS would search 1 first and then in queues 2 and 3, and then DQ2 in Q4 and 5, DQ3, and in Q6 and 7. So the order is basically 1, 2, 3, 4, 5, 6, 7. So again, do it on a small tree, and then you'll see that it's just doing stuff in order. So you'll traverse through all of these in order, and then at the end, you will in Q and DQ this 10 to the power, I mean 2 to the power 10. So that's why we have all of them basically. So all 2 to the 10 states are expanded. However, for DFS, you just push 1, push 2, pop 2, push 4, pop 4, push 8, and so on. So basically, you are just doing this. So suppose we want to know how many states we expanded for 4, then we have expanded 1, 2, and 4, so 3 of them, and it's power 2, and 4 of them if it's power 3, this is 3. So if you have power 10, it should be 11 of them. So again, do it on a smaller tree and find the pattern, and then you can see how many states expanded for the larger tree. So the next one is just basically repeat the same problem for 2 to the power 10 minus 1. So basically, you don't have this. So using the same logic, same pattern, BFS is going to search everything. Also, DFS is going to search everything as well, because that's basically the last entry that's searched for DFS, because everything needs to be searched before this state. So we're searching all of them as well. Okay, so the next one, let's see. The initial state is 1, the goal state is 5. So let's actually draw this. So this is kind of hard to read. So 1, 2, 3, 4, and 5. 1 can go to 2, 2 can go to 3, and all of these are 1. So this is 1, 1, 1, and 1. 1 to 3 is 2, 2 to 4 is 2, 3 to 5 is 2. So these are 2 to 2, and 1 to 4, 2 to 5, they are 4, and of course you have directly go from 1 to 5, and this is 8. What's this doing? So the question is asking to find the expansion sequence for uniform cost search. So we use a priority queue, and we use G as the priority. The smaller the G, the higher the priority. So let's start with 1. G is the cost so far, so nothing happened yet. So we put 0 here, and then we DQ 1. And then what are the successors? All of them are successors. So 2, 3, 4, and 5. They're all successors. And 2 from 1. So let's actually do all of them from 1. So the subscript here is where it's from. So 2 from 1 is 1. 3 from 1 is 2. 4 from 1. You can directly read from the table as well. It's 4 and 8. So they are correct in this order. That's good. Next step, DQ2, and then all of them are the successor of 2, so we need to replace all of them. Let's actually write them here. So 3 from 2, 4 from 2, and 5 from 2. 3 from 2 is 1 plus whatever this number is, so 1 plus 1. 4 from 2 is 2, so 1 plus 2. 5 from 2 is 1 plus 4. which ones needs to be updated. So here is the same number, so let's just get rid of this. Here, seems to be smaller, so let's replace it by 3. And here is 5, so let's replace this by 5 and get rid of that. And we should probably update the subscript too. Okay, so let's continue with this DQ3, and again, all of them are successors. So 4 from 3 and 5 from 3. 4 from 3 is 3 currently is 2, so 2 plus something. So 4 from 3 is 1. 5 from 3 is 2. Do we need to update anything? 3 and 3, so not updating. And 4 is less than 5, so let's update it. So this should be 4, and this is updated to 5 from 3. Okay, continue with this. DQ4 and add 5. 5 from 4 is, we have 3 so far, and 5 from 4 is 1. So plus 1 is still 4, so let's not worry about this. So we're done basically. The last step is just DQ5 and we're done. So the end result is just 1, 2, 3, 4, 5. The next thing is using this heuristic and do the greedy search. So the greedy search is also priority queue. It's the same idea, except for it's using H as priority. So let's start with 0 and DQ 0. Where is 0? Oh, so sorry, there is no 0. Start with 1 and H is 4 and DQ 1 and you add all of them. So when you add them, you don't use the G anymore. You don't care about what happened so far. You just use the estimated heuristic, and this is 2. So we're putting them in the wrong order. So let's do them again. So it should be 5, 4, 3, 2. So 5 corresponds to H value 0, 4 is 1, 3 is 2, and 2 is 3. So now the next thing we pop is 5, and then we pop the goal state. So we're done. So it's 1 and 5, and 5 is actually from 1, so we're actually getting the wrong answer. So it's okay. It's just asking for the greedy search expansion sequence. So it's 1, 5, and before we move on, let's figure out what H star is. So H star at 1, let's actually do H star at 1. Let's just write it this way. From 1 is the shortest distance to 5. We solved this so far. It's just 1, 2, 3, 4, 5, which is 4. From 2 to 5 is, you can do 2, 3, 4, 5, which is 3, or you can do 2, 4, 5, which is also 3. So in any case, the smallest one is 3. So 3 to 5 is 2 for the same reason. 4 to 5 is 1, and 5 to 5 will be 0. So that's actually, so the one here is actually the H star. So that's good. So we know that H star is 4, 3, 2, 1, 0, corresponding to states 1, 2, 3, 4, 4, 5. The first row is the state, the second row is H star. So now we want to see how many of these are admissible. Admissible means smaller than or equal to this row. So let's do it for each one of them. 5 minus I. So now I is the state. Let's call it I. So when I is 1, 5 minus 1 is 4. 5 minus 2 is 3. So it happens to be the same. So this is equal to H star. So of course this is admissible. And this is square root 4, square root 3. So square root of an integer is less than the integer. So this is okay. And this is slightly harder. So this is log 6 minus I, so log 5, log 4, log 3, log 1, and that's not right, log 2, and log 1. So the thing you should remember is log 1 is 0, so that's okay. Log 2 is 1, so that's okay. Log 3, it seems it's less than 2. So because log 4 is 2, so this is less than 2, so it's okay. Log 4 is 2, so okay. Log 5 is less than 3, so because log 8 is 3. So that's why all of them are okay. So again, this thing is admissible. And next one, um, 1 minus whether it's 5. So except for it's 5, this is 0. So it's 1 minus 0 is 1, 1 minus 0, 1 minus 0, 1 minus 0. And when it's 5, it's 1 minus 1. So this is 0. Let's compare. 1 is less than 4, 1 is less than 3, less than 2, equal to 1. 0 is okay. So this one is okay too. Heuristic being 0 is always okay. So that's why there are 5 of them. Okay, so let's move on. Which one is not dominated? So if you have H star, then for this particular question, H star is of course not dominated. So if we don't have this, then we would just compare each row, and if one row is completely larger or equal to another row, then that row is that first row, the larger row dominates the smaller row, so the smaller row is dominated. So here, I guess the second row would dominate the third one, and the third one would dominate the fourth one, and the fourth one would dominate the last one. So, but if you have H star, then of course nothing dominates H star. I mean, nothing admissible dominates H star. So there might be something that's not admissible, then being larger is not relevant. Okay, so let's move on to this. So we want to start with 1 and exit at 16. So this is basically the homework. So programming homework, and remember to count both initial and goal states. So let's actually draw this maze. So 1 can only go to 2, so there's a wall here. 1 cannot go to 5. 2 can go to 1 and 3, so 2 cannot go to 6, so there's a wall here. And 3, for the same reason. 4 can go to 3 and 8, so we're not stuck. So 5 can go to 6, so we have this boundary here, and this, and this. There's no this. So 8 can go to 4, 7, and 12, so there's no wall here. And this, and this. So the maze is basically you have the outer boundary, obviously, and you are entering here, you are exiting here. So that's what it looks like. What is this asking? Oh, IDS. Mm. So the path from 1 to 16, it's has length 7. So IDS will search everything with length 6, and we can count them, but that looks, if the maze is more complicated, that looks difficult to do. So let's actually draw it as a tree. So 1 goes to 2, goes to 3, goes to 4, goes to 8. 8 can go to 7 and 12, and 7 can go to 6, 5, 12 can go to 11, and 16. 11 can go to 10, and 9. 16 can go to 15. Well, we don't really care. Okay, so if you draw it like this, it's actually very simple. The IDS will just go through everything with length less than, with depths less than the depths of the goal state, which is all of these, and then it needs to search from left to right at the same level. So it will search 16, I mean 6 and 6 and 11 as well. So let's count all of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's why the answer is 10. And so again, IDS would always go through everything with depths less than the depths of the goal state, and at the same level as the goal state, it will do DFS. So if say 16 is say here, then it will search only one at that depth, but now 16 is the largest one at this depth, so we need to search 6 first, and then 11, and then 16. That's why the total is 10. And let's continue with UCS. So UCS with uniform, let's not call it uniform cost, with constant cost is the same as BFS. So in BFS, we just search it level by level. So we actually need to search all of these for exactly the same reason. So that's why it's also 10. Now we want to figure out A star. So A star, we are just searching the closer one first, the ones closer to the goal state according to the Manhattan distance first. So where are the choices? So here, 8, at 8, we need to decide whether we search 7 first or 12 first. So that would be one decision. 12 is closer in Manhattan distance to 16. The Manhattan distance from 12 to 16, so H is 1 here. For 7, H is 2 plus 1, so it's 3 here. So I'm going to search the one with smaller h, because so far g is the same. G is just the distance from 1 to 8, which is the same, and h is smaller for 12, so it will search 12 first. So for the same reason, compared to 12 to 11, it will search 16 first. So that's why A star will just search 1, 2, 3, 4, 8, 12, 16, and there are 7 of them in total. So if you actually want to draw the queue, it's possible as well, because there are only basically 7 states to expand. So now we move on to local search. So what are we doing here? At the beginning, they are all false, and remember the neighbor are the ones with only one variable flipped, and we want to solve first choice hill climbing, and we're finding the minimum number, I guess. So we are finding the minimum number of steps. If we are finding the maximum steps, then it's infinite because we can just go back and forth. And here we're finding the minimum number. So minimum number means the best case, means the luckiest case. So luckiest case is just flip one of them, flip another one, and flip until everything is just flip the same number of things that should be true. So the problem is basically reduced to solve this and get the minimum number of x being true. So we want to solve this while we minimize the number of x is true. So one trick is to look at how many times each x appeared. So x1 appeared 4 times. So probably when x1 is true, then 4 of them will be satisfied because none of them has a not in front. So remember, there might be a not in front, then you should not count that. And then you can just do any one of 2, 3, and 4, then say x2 is true, then the whole thing will be true. So we need at least 2, is that right? Is there any variable that appears in all of them? And if you look at these, there are not. So none of them appeared in all of the clauses, so we need at least 2 of them being true. So the first choice, hill climbing, the luckiest version, since first choice hill climbing is picking a random neighbor, so we don't know which one yet. We don't actually know which one to pick. I mean, we don't actually know which one is picked first, but the minimum number is the luckiest case. So x1 will be flipped first, and then x2 will be flipped. So that will be 2 steps. The next one is the the reproduction probability question. So I updated this formula. This formula was incorrect. So now I think it's correct. It's finding the minimum t. So it's the first time when xt is 1. So that's actually very simple. It's just the first time it's 1. So here it's 3. Yes. And here is 2. And here is 3. And here none of them is. And x6 is always 1. So the answer is 6. And these are the fitness, basically. So the reproduction probability, you have a formula. It's just the fitness of that one. Which one are we finding? State A. So of that one, divide by the sum of all of them. So this should turn out to be 3 over 14. And the next one is you add a state E, and the probability of reproduction probability of xt becomes 1 over 3. So what's the reproduction probability of x3? I mean xt. It's this one. So it's 6 over the sum of all of them. And the last one is a question mark. So that's the fitness of E. This should be 1 over 3. So you can solve this. So 18 is equal to, what's this, 14 plus question mark. So that question mark is should be 4. Okay, so now we are here doing the bargaining question. So we have a cake with size t, and each time kid 1 would, what was happening? Kid 1 would propose, kid 2 accept and or reject, and then kid 2 would propose, where is it? Kid 2 would propose, and kid 1 would accept or reject. So the difference between this and the Rubinstein bargaining problem we did in the lecture is every time that would just eat one piece. So at the beginning, there are t pieces, and after the first round is t minus 1, and then becomes t minus 2 after the second round, and so on. So that's the only difference. So we'll solve the problem the same way. So let's begin by draw the diagram. So kid 1 will propose, and say the proposal is x and 1 minus x. Then if I accept, the first kid will get 1, the second kid will get 1 minus, actually not true. When t is 2, it's 2 minus x. So that's the first round. And then move on here. The decision is made by 2, and this decision is made by 2. And again, I can accept and I can reject. Now if it's accepted, then suppose the proposal is y and 1 minus y. Then since the size here, at the beginning the size is 2, here the size becomes 1. So the total is 1. So if I propose x to player 1, then I will get 1 minus, y to player 1, then I will get 1 minus y. And at the end, we're assuming the dad would eat all of them because the size will be 0 here. So there's only one way to divide 0. Okay. So let's solve the same way as well. When would I accept? That's the question to ask. So who is deciding? So 1 is deciding to accept or not. So player 1 would accept if and only if. If I accept, I'll get y. If I reject, I'll get 0. So I'll accept if y is larger than or equal to 0. So 2 will propose something such that 1 will barely accept and 2 would want to maximize the amount of cake he or she gets. So would propose the least amount possible while it's still larger than or equal to 0, which means it is just 0. Okay, then let's move backwards. So here, 2 is deciding to accept or reject. So 2 would accept if and only if. Let's decide. So if, say I'm 2, if I choose A, I'll get 2 minus x. If I choose R, then I will propose 0, and then I will get 1 minus 0, so I'll get the whole cake. So I would accept if and only if 2 minus x. If I accept, I get 2 minus x. If I reject, I get 1 minus y, and I know y. So I'll accept if and only if this is larger than 1 minus y, which turns out to be y. So then we go back again. One will propose in a way such that this thing will be barely accepted. So let's simplify this. This just says x is less than or equal to 1. So one would propose something that gives himself as much as possible while getting this accepted. So the largest x such that x is less than or equal to 1. So x, I mean, 1 will propose x equal to 1. So x equal to 1 means the total size is 2, so it's 1, 1. So that's why this is the answer. Okay, so let's go through the same thing with 4 period. So hopefully we don't need to draw all of them. So 1 first, and accept and reject, 2 decides. So the important thing is who is deciding and what's the payoff. So x and 4 minus x now. And here, this is 1. And this will be y and 3 minus y. And this thing will be a 2-period game. So basically, I don't want to redraw this. First, there's no space to draw. Second, it's waste of time because this is just this thing put here. And so it's the same. So I can copy this whole thing here. And but that information is actually not useful because I know that at the beginning of that game, player 1 will propose 1, 1, and that's actually accepted. So the outcome of that is just 1, 1. So let's not copy anything, just put 1, 1 here. Okay, so now we solve the same thing again, so I'll not write it down because I don't have any space to do it. So here, 1 is making the decision. So 1 would accept if and only if I compare. If I accept, this is reject, I'll get y. If I reject, I'll get 1. So I'll accept as long as y is larger than or equal to 1. So that implies 2 will propose 1. And that implies now 2 is deciding if I accept, I'll get 4 minus x. If I reject, I'll follow this path. I'll get 3 minus y. And y is 1. So let's write it down. So 2 will accept if and only if 4 minus x is larger than or equal to, again, if I accept, I'll get this. If I reject, I'll get this. So these two should satisfy this condition. And y we solve to be 1, so this number is 2. So at the end, the last step is 1 would propose barely enough such that this is accepted, so x will be equal to 2. So here, if you solve this, you get x less than or equal to 2, so 1 will propose x is 2. So at the beginning, x is 2, so this becomes 2, and 4 minus 2, so it's 2 and 2. That's the answer here, 2 and 2. So if you cannot convince yourself that that's the pattern 1, 1, 2, 2, 3, 3, then you can solve another round for t equals to 6, and then you'll see 3 and 3. So hopefully then you'll be convinced when it's this number is just half and half. So half of 1024 is 512. Okay, so finally this is done. Let's move on to the next one. Okay, this one is a game of chance. So we have the main player plays first, head or tail, and then a fair coin is flipped. So this is chance, and this is chance as well. Head and tail, head and tail. And max player observe the outcome would choose head or tail. So let's draw it here. head or tail. This is the max player, and this is head or tail, head, tail, head, tail. Okay, so let's go backwards. So when you are solving this, whenever you see a max, you just take the max of the successors. And whenever you see a chance, take the expected value. Whenever you see mean, just take the minimum. So at the end, let's figure out first who wins. Who, what's the condition for winning? So player 2 or the max player wins gets, gets value 1 if all three actions are the same. So here is H, H, H. So all three actions are the same. So max wins, otherwise max loses. So here max would lose because it's HT. They are not all three of them the same. So this is -1. TTH is losing. TTT is winning. So max is always picking the max among these two. So max between 1 and -1 is 1. So I'll do this. Max between -1 -1 is the same. So either one is okay. I just copy the number -1. So this is 1 here. And again, this is -1. Max between these two is 1. So I copy the 1 here. Whenever we see a chance, we do the expected value. So half of the time I get 1, half of the time I get -1. So it's 0. So 1 times a half plus -1 times a half is 0. So the same thing happens here. I get 0 as well. So now it's the mean player. The minimum between 0 and 0 is also 0. So that's why the value of the whole game is 0. Okay. So the next one is just drawing the game, and then you should be able to see. So first action 1, 2, 3. Who's playing first? Max is playing first, and then Ming would do 1, 2, 3, 1, 2, 3, and 1, 2, 3. So now we compute the numbers. 4 minus the first one is 3 times 3 is 9. And so this is basically 3. 3 times 2 is 6. 3 times 1 is 3. And now this is 2. 2 times 3 is 6. 2 times 2 is 4. 2 times 1 is 2. Is it right? Yes. So now this is 3. 4 minus 3 is 1. So 1 times 3 is 3. 1 times 2 is 2. 1 times 1 is 1. Okay, so now we get all the numbers. And then we can do alpha, beta stuff. So here, the first one, I need all of them. So comparing these three, the minimum is 3. So we know the beta is equal to 3 here. And we go back and find the alpha. Alpha should be larger than or equal to 3. Okay, so the next thing is to search this. The first branch is always searched. So now beta is less than or equal to 6. Because the beta value is the minimum between these three. So when the first one is searched, then when the first one is searched, we only know that it's less than or equal to 3. I mean, less than or equal to 6. So now alpha is 3, beta is 6, nothing happens. We will stop if alpha is larger than or equal to beta. So now that didn't happen yet. So we do search 4. When we search 4, it's updated to 4. Still nothing happens. 4 is larger than 3. So now it's updated to 2. So all three of them actually needs to be searched. So we didn't prove anything. So now we get beta is equal to 2. And now we update this alpha needs to be larger than or equal to 2. That's actually not right. Alpha is still larger than or equal to 3 because alpha here is larger than or equal to 2, but it's already larger than or equal to 3. So it's keep it like this. Okay, so moving to the last one. Beta here is less than or equal to 3 because this is a minimum player after I search 3. So now alpha is equal to beta, so we can stop. So what it means is the max player can guess 3 from this already. And here, if the max choose to choose this right action, choose the action 3, then max can get at most 3. So it's possible it's less than 3. So max does not really care how bad it is. So I'm not going to search for the max player. The max player will not search, will not care how bad it is, less than 3 it is, because max player can get exactly 3 from action 1. So that's why the whole thing is pruned. That's why two of them are pruned. This branch and this branch. Okay, so next one is finding the states that survive iterative elimination of weakly dominant strategies. So here is weakly dominant strategies, which means as long as one column or one row is completely less than or equal to another column or another row, then that column or row is eliminated. So for example, 0, 0, 0, 0 is equal to 0, 0 is less than 1, 0 is less than 2. So this row is completely dominated by the first row. So this will be removed. And similarly, the last row will be removed. That's the row player, the max player. And the column min player is trying to minimize. So these two are removed. So the only one that survives this is U and L. Let's see. Oh, it's only asking for number, so there's only one left, and it's U L. And it's asking for strictly dominated strategies. Let's erase all of them. And if you look at the rows, then there won't be any row that's strictly dominant another because all of them here are 0. So there's no way one thing is strictly larger than another. So there's no way. None of them are strictly dominated. Similarly, there's one row of 0. So no column can strictly dominate another. So there's no way you put the strictly larger sign this way or this way. So nothing is strictly dominated. So nothing is eliminated. So that's why all 9 of them would survive. So again, the question is asking for how many survived. So the last thing to do is the Nash equilibrium. So which one are the best responses? So fixing the min player playing L, the max player, the row player needs to maximize. So all 3 of them are the maximum. And here, compare these 3 numbers. Given that the min player is playing M, I'm going to maximize. I'm going to select the largest number and do the same thing for when min player is playing R. I'm going to maximize. I'm going to play 2. So let's use another color. So for the column player, fix each row. So suppose the max player is playing U, then I'm going to minimize. So I'm going to do this. And here I'm going to do 1, 2, 3. They are the same for me. And fixing the max player playing D, I'm going to minimize. I'm going to choose this. So the cells with 2 circles are UL is a Nash equilibrium and ML is also a Nash equilibrium. So now you see that if you eliminate the weakly dominant strategies, you are actually eliminating one of the Nash equilibria because this is not in the set of iterative elimination of weakly dominant strategies. So going back to the question, UL and ML, these are the 2 Nash equilibria. Okay, now the last 2. We have a table like this. We will do the same thing. So fix the other player playing L. I'm going to, both of them are max, right? Yes, both of them are max. So this is 1 and this is 1, 1, and fix each row. Suppose the the row player is playing U, then take the max between these 2 numbers. This takes the max between these 2 numbers. They're the same. So circle both of them. Actually, 3 of them are circled. So B, C, and D, they are all Nash equilibria. So to write it out completely is D and L, D and R, and U and R. So all of them are are pure strategy Nash equilibrium. So now let's check which ones are mixed strategy Nash. So as you can see here, these looks like half of it's mixed, so it's not both players are mixing. So we need to check whether there are mutual best responses. So first, the easy way to check this is start with this. So the column player, I mean the row player is playing U, and the column player's best response would be if I play L, I'll get 0. If I play R, I'll get 1. So 1 is strictly preferred, so the best response should be R. It's not this, so the first one is not a Nash equilibrium. Let's do the second one. And if the, let's see, erase all of them and change their color. If the first player, if the row player is always playing D, then if I play L, I'll get 1. If I play R, I'll get 1. So I'm indifferent. So indifferent means any mix is the best response. So it's best response. So in particular, this mix is a best response. So we're okay on this side. So now we're going to fix this and then see whether always D is the best response. And let's actually check that. If I do half of time L, half of time R, then if I choose U, let's compute it. If I choose U, half of the time I'll get 0, half of the time I'll get 1. So it's half 0 plus half 1, which you get 0.5. If I choose D, it's half of the time I'll get 1, half of the time I'll get another 1. So I'll get 1. So D is preferred to U. Actually, I will always choose D. So they are mutual best responses. So now this is our first Nash. Let's do it again for the other ones. If I pick always L, I will get, I mean, if the column player is playing always L, then the row player is getting 0 from U and 1 from D. So I'll choose always D is the best response. So in particular, whatever this is not the best response. So this is not a Nash. They are not mutual best responses. Let's check the last one. If the column player is always playing R, then if I choose U, I'll get 1, this one, not the second one. So for the row player is the first number. So I'll get 1 from U and I'll get 1 from D as well. So I am indifferent. So in particular, any mix is best response. So this is the best response. Let's check the other way. So this is half of time I'm going to choose U, another half of the time I choose D. So I need to compare L and R. So for the column player, if I pick L, I will get, sorry, L means I'll get 0 half of the time and 1 half of the time. So half 0 plus half 1 is a half. And if I pick R, I'll get half of the time I'll get 1, half of the time I'll get 1. So half 1, half 1. So this is 1. So I'll always pick R. And yes, indeed, I am always picking R. So there are mutual best responses. That's why this is also a mixed strategy Nash. That's why the answer is 2.